right, welcome. Happy Thursday. Good afternoon. Okay, so we were talking about a couple of different classification methods, so we'll do a quick recap. But then I want to start talking about, okay, well, I've got these models and that's great, but how do I evaluate these models, right? So we'll kind of start with some review. And I feel like there's something I wanted to say, but I can't remember what it was, so that's okay. Can't remember. So for a little bit of review, right, we talked about classification, which is really predicting the class for categorical outcomes, right? And we decided to really focus on binary outcomes, but of course it goes for more than 2 outcomes, but it's just easier to introduce these ideas with just 2 outcomes, right? And we already know that, okay, even if I have multiple categories, there's usually one that I'm interested in, right? And so then I can make that my class 1, right? And everything else can be class 0. It really depends on the question, but a lot of the time we can get away with just making it binary and just applying these exact same methods. Okay, so we talked about classification, which is really just predicting for categorical variables. For categorical variables, specifically binary variables, right? Binary variables are categorical variables, right? They're 0, 1s. And so what do? Well, all these models, right? We introduced some common models, some common classification models. Things like, well, we talked briefly about the exact Bayes, but maybe we'll just focus on the naive Bayes. We talked about linear discriminant analysis, which we abbreviate LDA. And what else did we talk about? I feel like then we went to logistic regression, which is kind of our main player here, logistic regression. Here's kind of the one to focus on, right? And what does logistic regression do? It leverages our knowledge about, okay, well, I know how to fit a linear model, but if I have these 2 categories, I can't really do that, right? And so what we do is we transform the outcome, right? So it's no longer on a 0, 1 scale, right? And so we model the logit, or the log odds function, and then we can apply a linear model to that, right? So it makes the actual interpretation a little bit more difficult, but the modeling itself becomes a lot easier. So it's kind of a trade-off. But the logistic regression, right? It predicts the log odds, or the logit, right? So you'd have to kind of undo it, right? So it predicts the log odds, which is the log odds, the odds that y is 1, is beta naught plus beta 1 x1 plus beta 2 x2 all the way up to however many predictors you want, up to q predictors. Okay. And so what we would do, right, is that this is a linear function, right? So this is a linear regression, a multiple linear regression. It's linear because we're adding up all these terms. We can incorporate things like interaction effects, right? All those things come back into play, right? And so we said, all right, this is a multiple linear regression. So the coefficients, the estimates for the coefficients, they're the same as before, right? We've got p-values for each of the coefficients to tell us, okay, is this contributing to the model significantly or no, right? And so we can still work with that. The only hiccup is that, okay, well, my predicted value is no longer just the probability of being in some in case 1, it's going to be the log odds of being case 1. So we have to undo that, right? And so P, or technically P hat, but P hat, let's say, is 1 over 1 plus e to the negative y hat, where this is going to be your y hat. So you can still be given some values of x1, x2, x3, x4, and you can still plug them in and you can still get a predicted value of y, right? But that y hat has to be undone to get to a predicted value of the probability of being in case 1 or being a 1, right? And so here you have to do a little bit of BEDMAS work, right? E to the negative and then the y hat, right? And so, and then add it to 1, and then 1 divided by that number. Okay. So each of these, I just saw there's someone else in here with me. I had you covered by my chat. It's fun to get to see someone. I'm not just talking to myself anymore. It's a lot of pressure on you though. You have to laugh at all my jokes and you have to nod and make sure that I think that you're understanding. It's like sitting at the front of the class. All right. So yeah, no pressure, sweat emoji. So each of these, right? Each of these models, they don't just tell us if they're in case 1 or case 0, right? They're going to give us some probability of being in case 1, right? So each of these models, return the probability of being in case 1. Return the probability of being case 1, right? Which is the one that we're interested in. Okay. And then it's up to us, right? We talked about, okay, well, I can adjust the cutoff and I can you know, have a 0.5 cutoff. If the probability of being in case 1 is less than 0.5, then you're case 0, right? I'm going to call you case 0. And if it's larger than 0.5, then you're going to be case 1, right? Or if we want to be a little bit more sure, then maybe we up it to 0.8, right? But there's that trade-off between altering my cutoff, right? And so then we use these probabilities to classify or to predict whether it's case 0 or case 1. To predict whether each case is 0 or 1. Okay, and I should probably mention the cutoff. So no period quite yet, using a cutoff value. We talked about that last day, and we're going to see more of it today. So that's why I'm going to kind of parking lot it for a little bit and pick up where we left off. And so we introduced these 3 main ways that we could model, but our main one is going to be logistic regression, because it relies on all the other multiple linear regressions that we could make, right? I could look at just X1, I could look at X1 and X2, I could look at just X2, right? It opens up, there's a lot of models involved here, whereas these 2 are kind of boring. We're going to look at them, but we're going to focus on logistic regression. The problem with logistic regression is that it's not fit by least squares, unlike linear regression. It's fit by what we call a maximum likelihood estimator. And that is, there's derivatives involved, so a little bit of calculus, and I'm sure Claude will make you do it. But for us, let's just know that that's what happens, and then we'll just kind of parking lot it. Let someone else teach you that. That's boring. I want to teach you the fun stuff, right? And so, although it might be refreshing to do some derivatives, right? But no, because what is the maximum? Well, let's kind of talk about it a little bit. The maximum, right? If I want to find the maximum of a curve, then that's where the slope is 0, right? Or the minimum, right? So if you're working with optimization, you want to find the top or the bottom, depending on the question. And then either way, at a peak or at a valley, the slope is 0, right? The slope of the tangent line is the derivative. So you can find the derivative and you can set it equal to 0, and then you can solve for the values that make that happen. And that's the maximum likelihood estimator. And honestly, optimization in general. I digress. So logistic regression is not fit by least squares, but by maximum likelihood estimation. MLE, which when I was little was how I would like coolly spell my name. MLE, Emily. So like, yeah. So little did I know it meant maximum likelihood estimation. It wasn't until way later that I figured that out. But anyways, so if we don't have least squares, then we're not going to have things like the RMSE or the R squared. So we're going to need to find other ways of figuring out how wrong we were or how well our model fits our data, right? And also its predictive abilities. So I'll put it on a fresh page here. So I should spell it all out. Logistic regression does not have an RMSE or the R squared, because remember what is the RMSE and the R squared? They all rely on the residuals, right? But if we have 0, 1 cases, those residuals are either 1 or they're 0, right? And so that doesn't help us very much, right? And so logistic regression does not have an RMSE, which is how we usually decide how well a model fits, right? Or R squared. Okay. So we have to develop, or we have other methods of evaluating the models. So we need other methods for evaluating the model. That's where I was going to end last day. And now we're ready to introduce how we can talk about, okay, how can we evaluate this model? I think intuitively we have a pretty good understanding of, okay, if I have a sample and I know if the outcome was 0 or 1, right? Did I have a success or did I have a failure, right? In some way, and I'm able to predict and I can classify. We understand that sometimes I'm right? A 1 really is a 1 and a 0 really is a 0. But if I have a 1 and I predicted it to be a 0, that's a different kind of wrong than if I have a 0 and I said it was going to be a 1, right? And so usually we're more concerned with the ones. And so we need to be able to pull those kind of wrong conclusions apart and talk about them in different ways, right? Because usually we're more concerned with case ones. They're probably more expensive if we mispredict them, or that's not a word. Well, I said it, so it is a word. Right, but if we draw the wrong conclusion, then that's worse than misclassifying as 0. Classifying, that's the word I was looking for. Okay, so how can we evaluate these classification models? Well, did I end our, oh, I did, end of our review there, good. Evaluating classification models. And I'm going to be completely honest here. The terminology is really boggy, and I have a hard time keeping them straight. And I mean, I'm going to get there. I have to memorize them, and you have to do the same, right? Because we need to be fluent with this. But for some reason, I have a heck of a time figuring out. So when I say things like specificity, sensitivity, precision, those might ring a bell from Data Science 300, if you took it with me. Right, oh, we're back to that. Yeah, we are. Right, so we've kind of seen this before, but let's just talk about it a little bit more. Doesn't hurt. Okay, so evaluating classification models. We can talk about the overall accuracy, right? But that's kind of boring, right? And it doesn't really tell us that much, right? Especially if there's a cost to misclassifying our group 1s or group 0s, right? And so the overall accuracy is something that we could look at, right? And so the accuracy is just overall, how many did we correctly predict? Overall proportion of correctly predicted cases, right? It's pretty boring, and it doesn't really tell us anything about our model, right? So the accuracy itself is something we can talk about, but not very useful. Okay. If you think about these rare outcomes, right, then it'll start to become clear why the accuracy is not really that useful, right? So if you have this rare outcome, right, so if we think about, you know, people at a bank, right, and so because I used to work with bank data. So, and you want to predict who is going to come in and close their account, because you want to be able to contact them and make it right and change things. You're not going to. Why? Because it's so rare that you have someone that actually goes in and closes their account, right? It's a rare case. Most people, if you consider bank data, most people are still using their accounts and they're doing weird things and they're buying stuff and they're, I was going to say selling stuff. I don't know, maybe, right? But money's going in, money's going out, and they're just happy customers, right? And so, and that's the majority of your database, hopefully. And then, but the ones that you're interested in, right? So the case one in this case are those people who churn, we call them, and they're going to be the people who leave, right? And so we have this very low number of people who actually leave, but those are the ones we're interested in, right? And so we call that a rare case instance. And so if I have a model and it predicts that, well, everyone's just going to stay, that's true, right? For a huge number of cases, that is true, right? So saying that everyone's going to stay, so everyone gets a 0, right? No one's leaving, that's great. Well, the accuracy is really good, right? If I predict 20,000 cases and 19,930 of those are correct because they're all zeros, and then the remaining, hopefully 70, I don't know what, I don't remember what number I said, right? Those 70 cases, well, they were incorrectly predicted because, well, I just made everyone zeros. Accuracy is good, but it's not very useful. Right, so we have that problem of these rare cases, and they're the ones that we want to get to. And I'll introduce some of the ways that you can deal with that as well. But first, let's talk about some better measures of evaluating these models. So it all hinges on what we call a confusion matrix. Okay, and so we can build a confusion matrix. And I kind of skipped the R. I shouldn't have. It doesn't look that much better. That's okay. So we can build a confusion matrix to separate our kind of correctly predicted cases from the misclassified cases. So we can build a confusion matrix to split our correctly classified cases from our misclassified cases. Okay. So this confusion matrix is gonna, and I think that's such a cute name for it. Like, oh, these guys are right, these guys are wrong, these guys are right, these guys are wrong. Well, what does it look like? Okay, here we go. The true classification. I can't write it all today. Let's put 1s and 0s, right? So that's truly what's going on. If we knew what was going on, well, then we wouldn't need a model, right? We're trying to build a model so that we can apply it to information where we actually don't know the classification. But of course, to check it, we have to check it against something. It's like having the answers in the back of the textbook, right? It's like, oh, I did it right. Okay, then on the test, then I'm pretty sure that I can follow that same procedure and get it right, right? Same deal. I always work from the solutions backwards. Otherwise, I train my brain to do the wrong thing and it doesn't help me at all. So anyways, so we've got our true classification and we've got our predicted classification. Okay, so our predicted classification can either be a 1 or a 0. And of course, how we predict these is going to depend on our cutoff, right? So our confusion matrix will change depending on our cutoff. Now I want to make a note of that here. Note the confusion matrix. Oops. Matrix. I can't spell matrix today. Well, there's a lot of things I can't spell today. So the confusion matrix will change depending on the cutoff. All right. The cutoff for classifying as case 1 or case 0, right? But I'll just call it the cutoff. Okay. If I predicted that it was going to be a 1 and it actually is a 1, that's good, right? That's a true positive. Let's abbreviate that as TP, toilet paper. No, true positive, right? Whereas if I predicted that it was going to be a 0, but it's actually a 1, what's that? Okay, here we go, right? We've got true positives, true negatives, false positives, and false negatives, right? So which is it? Here, I predicted it was going to be a negative, right? If a 1 is positive, then a 0 must be negative, right? So I predicted a false negative, right? So part of it is kind of wrapping your head around all this terminology too. False negative, which we'll call FN. And the reason I'm giving you these abbreviations is because I want to give the formulas for precision and specificity and sensitivity in terms of these TP, FN, TN, FP. And then I find that that's the easiest way for my head to wrap around it, but we'll see. You have to figure out what works for you. Okay, so if I predicted that it was going to be a 1, but it's actually a 0, that's a false positive, right? Okay, now we're on a roll here. So here I have a false positive, which we'll call FP, and oh, I almost gave it away, although you're probably already there, right? If I predicted that it was going to be a 0 and it actually is a 0, that's a true negative, right? And so here, this is a true negative, which we'll call TN. Whew. Okay. So I can have my predicted 1s is going to be the sum of the true positives and the false positives, right? But in either case, I predicted a positive, right? And I can have my sum of 0s. So my sum of the predicted 0s is the false negatives and the true negatives together, right? I can also talk about my class 1s, right? They were either classified as 1s or 0s, but in total, right, we have the total number of 1s and the total number of 0s, same thing. So we're going to have these marginal totals out here that we can talk about as well. But I didn't give myself enough space to do that. So I'm going to cheat and copy. Paste. Predicted. No harm, no foul. And then I'll just call this the truth. All right. And maybe what we'll do is let's clean this up and just have the true positive, false negatives. Should have just written the That's what I get for being lazy. Should have just rewritten the table. TP, FN, FP, and TN. Right, and then I can have my totals out here. Something like that. How I'm going to denote these totals are when y equals 1, right? Because that's, so the truth is if y equals 1, right? And so here I have y equals 1. And I know that's kind of weird, but it's the total number of cases where the truth was that it was 1. And then here I'll call this y equals 0. I don't know what to call this. I guess it's n. Doesn't matter. Here, I'm going to call this y hat equals 1. Right? Because y hat is still the predicted outcome. Right? And then y hat equals 0. Yeah. So let's see here. Okay. Here we go. Let's bring the confusion to the confusion matrix. That's the part that we supply, the confusion. Okay. So what are the ones that we're really interested in? Well, it's going to be how many ones did I correctly classify as ones, right? So the true positives over how many did I correctly place as ones, right? And so here, and that's going to be what we call the sensitivity, or if we want to be cool, I guess the textbook told me that data scientists call it recall. Well, that's fun. And then it kind of breaks it up because then you don't have sensitivity and specificity. Hey, is it R? So then it becomes recall, sensitivity, or sorry, specificity and precision, RSP. No. I thought it was going to be like an alphabetical thing. It wasn't. So the recall of a model, right? So this is how we assess the models, which we called sensitivity in Data Science 300, right? Because that's what the text uses. So if you've got that memorized, it's okay. You can just make the transition to recall, calling it recall. The recall is the true positives over the total number of true positives. No, positives, right? And so here, what's this? So the recall is how many did I correctly classify as ones? How many ones were correctly, or maybe I should say what proportion, because it's not how many, it's a fraction, right? So it's a proportion. So the proportion of ones that were correctly classified, right? Of all the ones. Right? The specificity is hard to say, but not hard to find. It's going to be the true negatives over those that are truly zeros. So it's kind of the flip side of the recall is the specificity. So if I want to talk about, okay, well, the zeros, what happened with the zeros? The true negatives are all the correctly classified zeros over all the potential zeros that I could talk about, right? So it's the same definition, but for zeros. Okay. So the specificity and
can you guys hear me? It's booted me out. Oh. Okay. Okay. Weird. Okay, I'm gonna try to join back in here. Why would it do that when my iPad is still on? They're on the same Wi-Fi. Okay. All right. We might start chirping.
This is so strange. Disconnect audio. There. Oh. Technology, right? Oh man. Can't live with it. Can't live without it. Okay. I think we're still okay. Yeah. This was your chance to, I don't know what happened. Missed opportunity. Okay, it might happen again though, so that's going to be your chance to duck out. All right, I'll keep going. I don't know what happened. Sorry about that. Hopefully you had a little break. Is it my internet? No, it's my internet, probably, but no, it's nice. Okay, so the specificity, my video is lagging. Uh-oh. Technology. I'm telling you, am I still lagging? This is my chance. I know, yeah, I just ended it. There, you guys are done for today. Very confusing. I'm not kicking you guys out. It's kicking me out. Maybe you guys are kicking me out. Anyways, is it still lagging? I don't know. Oh, so you can hear me, but if I do gestures, I'll have to go slow. Well, that's annoying. I'll just keep the same face, or try to. All right, let's just get through this, shall we? Yeah, that's weird. I'm trying to think of how to make it funny, but I wish the video came before the sound, because then I could look really surprised and just say something boring. What's she gonna say? Okay, maybe I'll try this. Just I'll stop my video and maybe it'll, I don't know. This was your chance, Hussein, to turn it off. How about now? Is it still lagging? Oh, dang. All right, well, don't look at me, just listen to me then. That's no fun. All right. Dang. I can't really restart. Then I have, 3 seconds. That's still pretty bad. Because then we'll have 2 separate videos, but maybe that's worth it. Okay, yeah, let's do that. So I will boot everyone out, but just join back in. We'll start fresh. Okay, to see if we can fix this. All right, so I'm gonna end this and then you can come back in. Or you can leave and then watch the part 2 of the video that I post, because it'll be 2 videos. All right, see you back here.